doctor here who wasn't very good and says, oh, you have this disease that little kids have. So what you have to do is buy new shoes and socks every day. I'm like, are you an idiot? And sometimes you have to say that because they really aren't thinking. So all I did, I said, okay, clearly my insurance here isn't doing any good. So I paid $50 to go see a dermatologist. In 1 minute, he said, oh, you have this thing. Wrote me a prescription for a solution to put on my feet for the bacterial infection. Within a week, it was all cured. So in fact, it was so bad I was taking a razor blade to my skin at night to cut it off. Okay. Anyway, that was an aside. All right, I got your attention now. Gram-positive, reflection of that thick cell wall. Gram-negative, thin cell wall. Very different coloration when you do the staining. Here's some samples of this. So what is this? Gram-positive, gram-negative, gram-negative. Okay, and we will, in lab, when you look at these, we have these set up as demo scopes, okay? And they are oil immersion, which means if you barely touch that stage manipulator, you will completely move it out of the proper field of view. Use only the fine focus, only the small outer knobs. If you use the coarse focus, it's out of position, okay? So, and it takes us quite a while to reset these. So please, when you look at the demo scopes, so you're not doing the gram staining, we have prepared slides that illustrate gram-positive, gram-negative, they illustrate various shapes of these. Please, fine focus only. Thank you. Okay? We have to go in and reset these up almost every lab period. It's not useful for you, it's not useful for us, okay? We have diagrams near them to help you identify them. So if you're drawing a bacterium that's, 50 micrometers big, you're drawing a clump of bacterium, you're not drawing individuals, okay? With respect to drawings, you want to add a title and the medication being used. The demo scopes all are 1000x, and one ruler mark is equal to 1 micrometer. It's called a micrometer. That measuring device is called a micrometer. Is at 1000x. Each ruler mark is 1 micrometer. That is also true for your microscopes. If you look at your microscopes, 400x is equal to 2.5 micrometers. And if you notice the direct relationship here is 2.5-fold. And remember, as you increase magnification, the distance it represents gets smaller or bigger. Smaller. And notice the direct mathematical relationship. 2.5-fold difference here, 2.5-fold difference there. So on the lab exam, I will oftentimes have a table with made-up values and say, you switch the objective from this power to this. How will these calibrations change? How will the field of view change, etc.? And there is that direct mathematical relationship. Just keep in mind, if you increase magnification, the distance this represents is decreasing by the same correlation. Likewise, the field of view getting smaller or bigger. Smaller by corresponding value, okay? Anyway, here's the illustration. This is how many of you make bread? Your students don't have time, right? Sourdough starter. Sourdough in New York tastes different than sourdough in San Francisco, various places like that. And it's in part because the way you make sourdough starters, you put a solution of flour, a little yeast, and sit it on the counter for a day or two. Various bacterial spores and yeast that are in the air will go into that solution. Usually has some sugars too. And as a result, you get a different population of bacteria and yeast in that sourdough starter, so the breads will taste different from different regions. This is just an illustration of that, okay? Now, bacteria are small. They tend to be about maybe 1 to 5 micrometers big is all. Eukaryotic cells tend to be larger, around 10. So let's just do a calculation here. You have a cell that's 1 micrometer cubed, okay? So how many protons are within that cell at pH 7? You should be able to do that calculation. The only thing I need to tell you is what the volume is, right? So there's the calculation for this. 1 micrometer is the same as 1 times 10 to the minus 4 centimeters. So that's a cube, so it's to the third power. So that's 1 times 10 to the minus 15 liters. With that information in pH, you should be able to tell me how many protons are present. So take about a minute to try to do that calculation. I didn't do it myself, so I'm quick to do it on the board. Anyone get the answer? Do you need to know temperature? No, pH is temperature independent. The volume, now the point is, will the volume change with temperature? Yes, you could argue that as you change the temperature, the peptide might expand a bit or contract a bit, things like that, but ignore that. Use this volume of 1 times 10 to the minus 15 liters. So who did the calculation? Anyone? Yes, what's your answer? 602. I came up with 60, so let's quick do this. All right, I may have done that wrong. We have 1 times 10 to the minus 15 liters, is that correct? Yes? What's the pH? 7, okay. 1 times 10 to the minus 7 moles per liter means I have 1 times 10 to the minus 22 moles. Is that correct? And then if I want to convert it to number of molecules, what do I have to multiply by? I've got this number, which is 6 times 10 to the 23, which is 6 times 10 to the 1, which is approximately 60. Is that correct? Yeah, okay. I actually don't like calculators. It's faster to do it by hand usually, okay? On the exam, you will not be allowed to use the calculators. But the math will be very straightforward, okay? Okay, now on the lab exam, I would tell you the volume. I wouldn't expect you to do that calculation, but I would expect you to be able to do the calculation if I give you the volume and the pH. Does everyone see how this works? Because it's concentration, moles per liter, right? Okay. All right. Now that you have this, go back home and figure this out if it was water only, filled with water only, okay? So what would you need to do to change that, to do how many water molecules present? So basically what you have to do there is this was the concentration of the protons. So the thing you're going to have to substitute is what the concentration of water would be if it was pure water, okay? So we're not going to do that now. Go back home and think about that, okay? I've asked this very similar question on the lab exam, but I might make it pH 5 or pH. I typically don't make it pH 9 because if you do the calculations, it's 0.6 molecules. It doesn't make sense, okay? So anyway. You don't have the slide, it's not posted, but I thought this was kind of interesting. Clearly, around World War II, penicillin was an amazing discovery. There are certain things in the history of mankind or science that really makes a huge difference, and the discovery of penicillin was one of them. For military use, it was first used because all the soldiers having infections and that, but it came to the general population. Penicillin cures gonorrhea in 4 hours. I don't think it was really 4 hours, but it was very effective. And now we have issues because many bacteria are resistant to antibiotics because of gene transfer between them. So right now, we're in a real situation where we have a lot of bacteria that are antibiotic resistant, and what do we do to treat them? So quite interesting. There are still, Dr. Downey will talk a bit about bacteriophage, which are these viruses that eat bacteria. They are now, there's a hospital in Russia that still treats patients with bacterial infections. They give them solutions of phage, bacteriophage, which will then kill off that bacteria and take care of the infection. And in fact, there's now proposed that these things that are antibiotic resistant, can we generate phage that would be effective treatment for them? Anyway, still lots of opportunities for people. Animal care and use, I'm going to go over this now, and hopefully this is going to work. And I mentioned that it's important that we think about the animals that we're using and show respect for them. There are 3 organizations on campus that deal with animal use and care. Okay, and the animals are very well treated. It's mostly vertebrates that get the specialized treatment. Invertebrates tend not to get specialized treatment, although we still have to have proper procedures in place. Focuses mostly on vertebrates, but it is definitely 3 groups. To use animals in the classroom, we have to justify them. We have to give them numbers of use. We have to explain what we're doing with them. That we look at alternative models, et cetera, et cetera. So please, there are various groups on campus that regulate this. So why do we use animals in research or teaching? They often have very useful models for various disease conditions, things like that. So, you could argue that it's not real ethical to, and it has been done in the past, to infect people with various diseases such as syphilis and then test various drugs against them. It's been done. It's not really ethical. You could argue whether or not it's ethical for animals as well, but it is one way to use race models to do race tests. It's part of the drug clearance procedure to test those. So various things like that. We will work with one vertebrate, which will be the rat. This is a publication that was in Life in 1966. It sort of started the whole process of this. I was in college one time, many years ago. I took an ethics class. It was taught by different professors. Mine happened to be a chemistry professor that I worked for. And I wrote a paper saying how, when we do various experiments with animals, that we should justify them. Various things. I mean, there's been some very cool things done to animals. And basically, he gave me a D on the paper because he said, I think we as scientists can do whatever we want with animals. The thing has changed. Things have changed, okay? It doesn't mean there still aren't abuses. And in fact, if you feel there's abuse, things like that, there are procedures to, contact people on campus, etc. But anyway, treat the animals with respect, and they deserve it, okay? But we do use them as models for various things. There are various laws and policies that have been put in place, monitored by various federal organizations and state organizations as well. As you know, various groups are very concerned about this, such as PETA, etc. But anyway, we do have things in place, various animal welfare regulations. Housing, caging. When we get the rats in, we have to order pathogen-free rats from specialized breeding facilities. They're closely monitored for disease states, various things like that. When we get them transferred here, we have to have them in special facilities, things like that. So there are various things in place. Temperature, precisely regulated, things like that. In fact, I have wanted... Okay, I'm going to apologize in advance. Please come to my office hours. I want you to come, but you might complain that it's really hot in my office or in the GSA office. And that's because for 10 years now, we really haven't had airflow. It comes on maybe once a month, whenever. So my office ranges in temperature from about 50 degrees when it's on to about 80 degrees. And that's in a span of maybe an hour. Bottom line is, I've thought about saying I'm going to put some rats in that room, because if I house rats in there, it would be under the control of OLAC, and it would be very precisely regulated. So, but I'm an animal, but I'm not under jurisdiction, okay? You're animals too, okay? All right? So anyway, food and water sanitation, a lot of things like this, precisely maintained. Training, we have to go through ethics training. We have to go through various procedures in terms of handling the animals, various things that we don't disturb them. So we do have an ACUC that reviews all of our procedures about what animals we're using, how often, for what purposes, things like that, okay? There are pretty much 3 things we think about. Replacement. Do we have another system or model in place? And the thing is about the dissections, you learn skills doing them. We are not talking about, I'm going to use a mouse, in terms of computer mouse, to make a dissection and make a cut. You can't control how deep you do that incision, racing like that. So you do learn skills by actually doing the dissections. Okay? The other thing is, we will occasionally have disease states or anatomical differences between organisms. So in lab, if you find something like that, raise your hand, point out to GSI, so we can point out to other students. Okay? So so there are some things like that. I know of no model that suddenly introduces some physiological change in frog, things like that. Okay? Reduction. We have done our best to minimize animal use. We try to dispose them properly, using as food sources for other organisms when we do, and refinement. So basically we go through, and when we go through procedures, we try to find specific ways to minimize the pain, deal with euthanasia, things like that, okay? So we are working hard on this, okay? The 4th R is respect. I addressed that the first time when I said, please don't name the rat and various things like that, okay? And you don't really need to be squeamish when you do the dissections. Treat it as science, you're learning some skills, things like that, okay? And then OLAC is one facility on campus. We have vets in place to do various surgeries. If you guys want to see an interesting, I think it's YouTube, do a search for chameleon changing color. How many have seen this YouTube? What they do it? You've seen it? Yeah, so we used to have a lab with this, and basically what this guy has done is he has various colored eyeglasses, and he puts the chameleon there, and it grabs the pink eyeglass. You can literally see the chameleon change its body color from pink, from where its front foot was on, to the back. And then he'll take the pink one away, put the green one. As it moves forward, the animal front turns green, pink here. He has 3 glasses. You can see pink, red, blue sort of things. Pretty amazing. So unfortunately, we don't do that lab anymore. I wish we did. We have specific things we follow for this, and if you have any issues, I know some of you don't like to do dissections, think of it as a learning tool. We're not going to force you to do the dissections. If for some reason you don't want to, pair up with someone who is very enthusiastic about doing them. If you have allergies to animals, please tell us. Especially if you have known allergies to cats or rats or mice or whatever, tell us, okay? I happen to be pretty allergic to rabbits. We used to have rabbits in the lab. I had to stop that because I was having reactions. So anyway, please tell us about these things. If you have a fear of cockroaches and you're going to be screaming and running out the door, tell us. We'll put you close to the door. We'll actually work with you to try to overcome some of those fears, but we are respectful of your fears, okay? So anyway, so we're not going to chase you with the cockroach or anything like that, okay? All right, and if you have concern about animal treatment on campus, please take advantage of this. There are things in place, okay? And again, you can read through this. And in summary, we do use animals, and please respect them as we work with them, okay? There is a reason why we work with them, okay? So now I'm going to go back to the rest of the slides. Let's pull this up. And we're going to the eukaryotes, okay? And I do hopefully want to have a little bit of time about what we're going to be doing in terms of the Vibrio stuff. And I have, okay, so with eukaryotes, they have membrane-bound organelles. That's what we used to say. Let's say in particular they have the nucleus, which is a membrane-bound organelle that contains the DNA. That DNA is usually linear and usually more than 1 chromosome. Prokaryotes typically have 1 single circular DNA. Eukaryotes tend to have more than 1, and they tend to be linear, okay? So we work from the outside. In this case, it's animal cells. We don't have the cell wall, but we do have the plasma membrane, that bilayer. Remember, the outside leaf of that bilayer, the outside layer, is very different than the inside. Different proteins there, sometimes different levels of cholesterol, different phospholipids, etc. So there is a difference in the topology between this outer and inner. And I'll illustrate this to you on the board lot of people ask me, how do I study for 1A? How do I study for the lab class? I think it's very helpful to make drawings. So what I'm going to do here is just draw one thing that illustrates this topology aspect of things. And I hope you can see I'm going to try to color code this, and the white chalk has disappeared. All right, so if this is the outer leaf, and this is the inner, if I have a vesicle approaching this, remember that vesicle itself is a bilayer, filled with contents inside it. So if I'm doing exocytosis, notice what happens. This will fuse with that. This is that membrane there. That will fuse with the yellow layer, and will dump the contents externally, or vice versa. If it was endocytosis going inward, it would be the reverse of that, okay? But remember, the topology is maintained. So this face that is facing the cytosol, when it fuses with the membrane, still has the same topology, okay? Part of the endomembrane system is to maintain that topology as it moves through the Golgi and the various organelles, okay? So one organelle there, so we have rough ER and smooth ER. Ribosomes are bound to the rough ER, making proteins embedded in the membrane and through the endomembrane system. If I have membrane-bound, do I have membrane-bound ribosomes in a prokaryote? Yes, I do. Now, where would they be? Plasma membrane, because that's really the only membrane they have, right? So there are indeed proteins embedded in the membrane of prokaryotes. They have to, for transport, receptors, things like that. As they are synthesized, those ribosomes aren't bound to the rough ER because they lack it. They're indeed bound to the plasma membrane, okay? So you can still get that topology aspect thing. There's still sidedness, whether you're a prokaryote, eukaryote. There's still the requirement for those proteins that are in membranes, typically, to go through a ribosome bound to it, okay? In terms of the rough ER or the plasma membrane. There's a cytosol, there's various organelles like mitochondria, in this case, no chloroplasts, we're talking about animals. Mitochondria, powerhouse, various organelles like peroxisomes, microvilli, etc. So you've read about that. The purpose of these membrane-bound organelles, compartmentalization. It's like a house, bathroom, bedroom, dining room, kitchen, etc., etc. Specialized function, so you have different things going on. And what they do is by making those compartments, they increase the surface area for a given volume. So we tend not to find huge cells, we tend to find very small cells. With some exceptions, some of your nerve cells may be a meter or two long, but usually they're quite small. We have an excellent example of this in the lab where cells that are quite large. And I'll put this on the board, it's one of the things you'll be looking at. So in terms of the prokaryotes, the exercise that you will be doing was looking at the gram stain. So looking for plus minus, looking at shapes of these. So there's three shapes, rod, round, or spiral. It's discussed in the manual. So you're looking at gram stain procedure, shape. The other group of prokaryotes will be the cyanobacteria, which historically were also called blue-green algae. I don't like that term because when we think of algae, we're going to think typically of eukaryotes. So don't use that term. But they are indeed a eubacterium. They're not an archaean. And we'll be looking at those, and they do have photosynthesis, so they typically are green in color. But they do not have chloroplasts. They don't have that membrane-bound organelle of chloroplast, okay? So with respect to prokaryotes, that's what you'll be looking at. With respect to eukaryotes, one of the eukaryotes that you'll be looking at will be Nitella. And I'm putting this on the board now because Nitella have huge cells, pretty much. Very unusual for these Nitella. The cells are huge. In fact, they're so large that for a molecule to diffuse from here to here via strictly Brownian movement, random diffusion, would take really a long time. So they have what's called cytoplasmic staining. They literally mix their entire cytosol to get this molecule to go over there in a short time span of milliseconds. Okay? If it didn't have that procedure, it'd take forever. Not forever. It'd take hours to days, which is just not acceptable to a cell. It would be dead. So we'll see excellent examples of cytoplasmic staining. That's the purpose of that, to do that bulk mixing. It's like when you make orange juice from frozen orange juice. You put it in the pitcher, you add the water. You can let it sit there and come back in a month, and maybe it will diffuse enough, but you just stir it to make it quick, right? So that's the same thing that's happening here. It's called cytoplasmic staining. And these cells are so large that it was very easy in the past. We can now do it with much smaller cells. Traditionally, these cells allowed us, because they're big enough, to go in with needles, suck out the fluid. And when you see things like there's this much calcium, this much potassium, etc. in these cells, it was historically done with these large cells like Nitella and various other ones, okay? Because it was easy to manipulate back then. We now have tools where we can look at small cells, okay? But anyway, keep in mind that cells are small. Keep in mind that increases the surface area relative to volume. And that just illustrates this. When we talk about the second half of the lab, when we're looking at actual animals, we will address some of these things because we will be looking at things that are small enough that they can rely upon free diffusion or simple diffusion. But we will look at other things like ourselves that are big enough that we have to have a circular system. We have to do the bulk mixing, that sort of thing, okay? We'll look at Hydra again, thin layers, so we can afford to do the time there for diffusion. Here's some of the protists you're going to be looking at. So I apologize, but the protists that you are looking at are not pure cultures. There are other things in those cultures because they will feed upon them. So when you're looking at the amoeba, that doesn't mean it's only amoeba. In fact, there are other things that they feed upon in there. So make sure you look at the figures in the lab manual when you're trying to identify things. The amoeba should look like the amoeba in the lab manual. The paramecium should look like the paramecium in the lab manual. And they should be about the same size. The figures always have scale bars in them. The purpose of the scale bar is to help guide you. Say, yeah, it looks like a paramecium, about the same size of paramecium. It's a paramecium culture. It's probably paramecium. Not 100% certain, but probably, okay? Is this clear? So this is an amoeba. I've seen lots of grains of sand drawn and labeled as amoeba. They don't look anything like that. Grains of sand, very rough texture. They look very different. They don't move. Etc. So just look at the figures. Now, here's the paramecium. They are very large, and these are really cool to watch. They have all these cilia on them, and you will add a solution of red-colored yeast. And the purpose of that is they will ingest the yeast. They'll feed upon it. And as a result, since these are rather transparent, you can see those red-colored yeast being ingested and formation of food vacuoles. So although you can't see the actual endocytosis that's occurring, but food vacuoles are food being taken